Good morning, everyone. Morning. Ketan sir, good morning.
Good morning, Rathod sir.
Good morning. Nice to see you, sir. In participants list.
Yes.
Sridhar, how are you? Sridhar Sahu. Sahu Saab.
गुड मॉर्निंग सर।
गुड मॉर्निंग, कैसे हो?
बढ़िया सर।
आज तो 10 आउट ऑफ 10 मिला के छोड़ दिया आपने।
सर पता नहीं, अभी तो देखा नहीं, उसको पे 8 बजे दिया था, अभी देखा नहीं।
Sir, Rathod sir.
हाँ सर।
This time score नहीं डिस्प्ले हुआ।
बंद होने के बाद दूंगा सर, बंद होने के बाद दूंगा। मैंने उसको थोड़ा एक्सटेंड किया, आधा घंटा एक्सटेंड किया, क्योंकि अभी उसपे करीबन 30 लोगों ने दिया हुआ है टेस्ट, मतलब बाकी लोग मुझे दे देना चाहिए करके उसमें आधा घंटा एक्सटेंड कर दिया।
Okay, so I think first STTP में as soon as we submit the score was displayed.
नहीं, वो पहले 2 क्विज को हुआ था, बाद में मैंने बंद कर दिया था।
Okay.
So, Naveen?
Today we have all Entuple session. Evening switch capacitor by Bhagini madam is there.
Yes sir. Actually, what happened is yesterday ma'am was supposed to the applications of mixed signal circuits, and then she was supposed to teach the basics of switch capacitor circuits, 1.5 hour.
Okay.
But then she covered the first part and second part was remaining. So madam requested in the session itself, she requested and she contacted me, so we had given today's 1 hour to her.
Yes.
Hopefully ma'am joins in the evening. So Naveen, shall we start? Are you ready?
Yes sir, we are ready sir. We are ready.
Okay. Sneha madam, can we go ahead? Yes. So good morning everyone to the second day of our third STTP. So today and tomorrow we have with us Entuple team, and we have 3 experts from the Entuple, Mr. Naveen, Mr. Sai Krishna, and we have Saraswati. All the 3, I think all of them have joined the meet now. So it's my pleasure to introduce Naveen Shankar. Is a field application engineer located at Bangalore at Entuple Technologies. He's working in Entuple since 2017. His role includes the logical and physical synthesis, placement and routing flow consisting of various steps such as floor plan, power plan, sanity check, placement, clock tree, synthesis, routing design optimization, etc. He has worked there for 2 years as a field application engineer for EDA products. He has supported on some of the design related queries at different levels like RTL, design RTL, synthesis, physical design, physical verification, etc. So I welcome Naveen you for this session, for 2 days sessions. Then we have with us Mrs. Saraswati. She is a PD engineer again at Entuple Technologies. She is a graduate from Electronics and Engineering from Vivekananda Institute of Technology, Bangalore. From the last 3 years, she is working on various cadence tools and the corresponding domains for training and support for academic sector plan, Pan India. She worked as a technical support engineer for cadence Entuple Technologies from 2017 to 2018. She basically is on ASIC physical design and verification. So welcome, ma'am. Welcome to S.P.I.T. and welcome to these sessions. Then we have with us Mr. Sai Krishna. He is also an application engineer at Entuple, Bangalore. He did his bachelor's in electronics and communication engineering from MLR Institute of Technology, Hyderabad. He completed his training and worked as a design engineer almost for 1 hour at Entuple Technologies Private Limited, Bangalore, and currently working as an application engineer for Cadence Bangalore for the last 2 years, handling various Cadence tools and corresponding domains for training and support for academic sector pan India. His area of work deals with basic physical design, synthesis, RTL coding, timing analysis, along with the considerable hands-on experience on full custom IC design flow. So it is my privilege to explain to welcome you all three, entire Entuple team, and looking forward for your sessions. So your sessions are planned from 10 o'clock to 1:50. So you can go ahead as per your, you can give the break as per your planning. Whenever you feel that there is a change in the plan and you have completed one aspect and you are going to shift to the next, you can give a break. So now over to you, Naveen. Thank you very much. Welcome.
Yes, sir. Thank you, sir. Thank you very much, sir.
So access rights I should share to you or Sai Krishna to me?
To me, sir. To me.
Okay.
Yes, sir. Is my screen visible, sir?
Yeah, visible.
Yeah. Thank you, sir. Thank you. So, good morning, all. This is Naveen Shankar, working as an application engineer for Cadence from Entuple Technologies Private Limited, Bangalore. Okay. So let us start with today's session. Okay, and we are into the VLSI design using Cadence tools. Okay, and STTP that is sponsored by AICTE in association with the S.P.I.T. Mumbai. Okay, and this current STTP program is on mixed signal VLSI design, as I've been going through yesterday's session also. Okay, so this will be the agenda for today's sessions. Okay, we'll be starting with an overview on full custom and semi-custom IC design flow. Okay, along with that, details will be given on Cadence tools. Okay, which are going to be the front end tools and which are going to be the back end tools in both full custom as well as semi-custom IC design. And as the special request was made on Rathor sir's side. Okay, and to help all the participants to have an idea, okay, of what are going to be the list of tools provided by Cadence. Okay, and then we'll move on into the next session, okay, which will be on synthesis and pre-layout STA. Okay, and then we'll move into the physical design and verification flow industry perspective. Along with that, you'll be provided with a demo on logic synthesis and a pre-layered STA using Genus. So, so session 2 and session 3 will be handled by Sai Krishna as well as Saraswati, okay, who are expertised in those particular domains. Okay. So we'll start with the session 1, okay, an overview on full custom and semi-custom IC design flow. And this will be the session agenda. Okay, we'll be starting with a recap on what we have done during STTP2. Okay, that was handled by VDK sir, Sijo, and myself. Okay, and then we'll move into the Cadence tool set, and then we'll proceed on with the overview on full custom and semi-custom IC design flow. So quick recap. Okay, VDK sir started by asking a question of what is electronics and communication engineering. Okay, and then about what is communication engineering and what are the main parameters that are being considered in when you go for any type of circuit design. Okay, and mainly we used to think on the application perspective of whatever circuits we are trying to create or build. Okay, and the STTP2 was mainly concentrated on analog circuit design and layout design, right? He started by giving an introduction of what are the types of signals, okay, that we hear or that we get in our day-to-day life. Okay, along with that, he explained about the typical signal chain for an analog signal processing system. Okay, and he gave us an introduction about a basic cell phone audio signal chain and the blocks associated with that. Okay, and then since we were trying to build an amplifier circuit, okay, he started with a brief introduction of what is amplification. Okay, he gave us some real-time examples, okay, and how a signal looks like. What are the factors by which the signals are amplified? Okay, and what is the acceptable level? Okay, uh, acceptable level of delay or phase shift. Okay, and when it goes beyond a limit, what happens to those signals? Okay, so these were all the uh, things or processes that were covered by VDK sir. Okay, and then we moved into how to build an amplifier. Okay, these are what is an amplifier and how it performs. Okay, when you design, what are the factors that are to be considered? Okay, and now comes how to build one. Okay, so we had went through an Ohm's law. Okay, there is some process of ideation that has to be taken care of. Okay, so we started with Ohm's law. Okay, and as we moved forward, okay, we were trying to get into the voltage controlled and voltage controlled current source and current controlled current source and current controlled voltage source, how it behaves. Okay, how is that related to an amplifier? Okay, and since we were making use on the MOSFET technology, okay, we were taken through the IV characteristics of MOSFET, and we were concentrating on all the four regions: cutoff, linear, saturation, and pinch off. Okay, and then we went into the evolving amplifier circuit topologies. Okay, where VDK sir introduced us to took us through the basic gain stage of an amplifier design. Okay, and then he showed us how the equation looks like for a small signal operation. Okay, of a basic gain stage amplifier. Um, and one more thing that we were taken through is GM by ID methodology. Okay, and then it was common source amplifier with a passive resistive load. Okay, the output resistance and gain. Okay, what is a major factor that major role it plays? Okay, in circuit design. And then we went on into the common source amplifier with a current source load. Okay, how was it designed? What are the factors to be considered? Okay, and then we moved into the differential amplifier circuit design. Okay, and then differential amplifier with a current mirror load. Okay, how it happens, how it works, what is the gain of this amplifier, how is it going to affect the other parameters of of circuit components, how is it going to affect the gain of the overall circuit. Okay, and then we went on into the two-stage op-amp circuit topology, how to get the how to obtain the gain of an input stage and an output stage, and then we went into the frequency compensation circuitry. Okay, and then these are the circuits to be designed, but how to design it? Okay, so we were taken through the amplifier design flow. Okay, we started with specification. In specification, we are supposed to look into what is the technology node, the constraints, okay, and once we have designed the circuit, we have to check for its performance, right? So performance specifications like small signal TC gain, 3 dB bandwidth, input and output voltage swings, slew rate, settling time, startup time, noise performance, input and output impedances, okay, all these things have to be considered, okay. So in this design flow, the step one is going to be deriving the design variables from circuit performance specifications, derive the device parameters corresponding to those design variables, size the MOSFETs and compute the bias requirements. Okay. Then step two was schematic capture on circuit simulation platform and analog simulation, and functional verification by checking out the DC and small signal AC analysis. Okay, and then physical design and verification through floor and routing plan. Okay, since we were working on analog layout, okay, we were also taken through the matching processes. Okay, and then we went on into layout engineering, DRC, LVS compliance check, parasitic extraction, back annotation, and finally post layout simulation and characterization of the design. Okay, so for all these processes, okay, that were addressed during the previous session, okay, what are the tools provided by Cadence, okay, is what we'll be going through. Okay, so brief introduction about Cadence. As you all might have known, okay, it is a pivotal leader in electronic design, building upon more than uh, 30 years of expertise, okay, in computational software design. Okay, the company applies its underlying intelligence system design strategy to deliver software, hardware, and IP that turn design concepts into reality. And their customer base includes consumer electronics, hyperscale computing, 5G communications, automotive, aerospace, industrial, and health departments. Okay, so Cadence offers solutions for semiconductor and system companies, okay, offering the broadest, most integrated end-to-end solution that includes silicon design creation, simulation, implementation, and sign-off of analog and digital circuits, off-the-shelf design IP and IC packaging, which includes machine learning enhanced EDA tools and machine learning enabled EDA flows. Okay. So when it comes to custom IC and PCB design, okay, we have certain processes like schematic capture that we were looking at shortly. Okay, schematic capture, simulation. Okay, then it comes to layout design. Okay, physical verification. Okay, and then we'll move into packaging. Okay, in packaging we have certain analysis concepts like um, signal integrity and power integrity analysis. Okay, so for all these things, okay, we have the tools, okay, that will help us for schematic capture. And for schematic capture we have the tool called Virtuoso, okay, which you can check it out here. Okay, so mainly concentrates on the chip design. Okay, so we have Virtuoso for schematic capture. Okay, and then for the simulation aspects, okay, the for the types of analysis, that is small signal AC and DC analysis, transient, and noise analysis. Okay, so we have a tool called Spectre. Okay, Spectre is a simulation engine which will help you in running through the circuit simulation. Okay, and then we'll be talking about the layout, right? So Virtuoso layout editor, okay, helps you in designing the layout. And for physical verification, once the layout is complete, you'll be moving into the physical verification, right? So for that process, we have the tool called Assura. Okay, Assura and PVS. Okay, is a physical verification system helps us in working on the physical verification. So the steps we have already seen. Okay, it will be DRC, design rule check, layer and layout versus layouts versus schematic. Okay, comparing your layout with the schematic and checking out whether all the interconnections, components, ports, input output ports are available, um, both in schematic as well as layout. Okay, so to check those aspects of your design. Okay, and once that is done, you will move into the packaging process. Okay, so Allegro helps you in those aspects. Okay, and uh, when you go for board level design, once you have fabricated your IC, okay, and you have to test it, right? So for that process you have a tool called Allegro, P-Spice and Arcad. Okay, so you can import the chip that you have designed, okay, and into Arcad, okay, and you can test its behavior. Okay, that will be a circuit level design and simulation tool. Okay, and for immediately after packaging, you'll be going into the signal integrity and power integrity analysis, right? So for that, you have the tool called Sigrity. Okay, and you will be having certain tools, certain circuits that will be required to be made use of in a digital system. Okay, since you are talking about mixed signal design. Okay, so you'll be designing certain standard cells like an inverter, for example. If you consider an inverter, okay, you'll be designing an inverter of different drive strengths, an AND logic, flip flop. Okay, so digital circuits, okay, will be designed in Virtuoso. Okay, and you'll be developing the library files. Okay, uh, like .lib, okay, which are liberate files. Okay, so liberate files or library files that will help you in getting the timing specification for the logic circuit that you have designed. Okay, so in order to develop those liberty files, okay, you need a tool called library. Okay, and the process is called library characterization. So liberate and variety helps you in characterizing the cells, okay, which has to be made use of in a digital system. Okay, and along with that, you need the LEF, okay, library exchange format files, okay, and DEF. Okay, so these are the files required for importing your design into a digital system, or in order to build a circuit using certain digital components. Okay, so this is about, and along with these tools, Cadence also provides you a wide range of flexibility. Okay, in order to make use of uh, advanced technology nodes like 16 nanometer or 18 nanometer or 14 nanometer FinFET technology, CNT FET technology. Okay, so it supports all the technology libraries. Okay, they can be brought into the Cadence tools, and you can make use of. You can build your circuits by making use of um, uh, through those technology libraries. Okay, Cadence supports all. Okay, so particularly for today's topic, since we are since the sessions are about mixed signal and low power mixed signal design. Okay, so you have two types of designing aspects. Okay, one will be analog on top, and the other one will be digital on top. Okay, so what you can do is you can start your design on Virtuoso. Okay, get the files. Okay, or create your Verilog or VHDL files. Okay, and then import it into Virtuoso. Okay, then build your layout. Okay, layout of analog systems on Virtuoso and digital systems on Innovus. Okay, and then combine both the things. combine both the things and complete the whole entire design. Okay, so in those aspects, okay, you have tools like tools that are binded with each other. Okay, so if you take cadence, okay, it will be binded along with the Innovus, Incisive, ZVM. Okay, so these tools are important when you talk about mixed signal design. Okay, and now coming to the digital design and sign off. So you'll be thinking about what are Innovus and what is Genus, Incisive, and all. Okay, so here we have the answer for that. Okay, so in order for design, okay, in order for design capture, okay, you have the tool called Incisive. Okay, which helps you in getting your program, okay, check its syntax and semantics, okay, before you move into technology specific implementation. Okay, and once that is done, okay, you will move into the design creation with the help of technology libraries, and Stratus, Genus, Modus, and Conformer will help you in design creation aspects. Okay, so Genus is the tool for synthesizing your program. Okay, that is your .v file is going to be converted into a block level or module level design. Okay, so Genus does that, and Modus will help you in DFT process. Okay, Genus and Modus together will help you in design for testability, and Conformal will help you in checking what are the additional nets or additional blocks that are included in your design. Okay, so mainly for uh, uh, basically to check the netlist files and bring out what is the differentiation. Okay, what are the additional blocks included to the design. And once you have synthesized the design, okay, you will move into the physical implementation. Okay, that is layout capture, okay, of that particular design. So Innovus helps you in those aspects. Okay, and then you will move into the electrical sign off. Okay, so you'll be checking about the timing aspects of the design, power aspects of the design. Okay, and when you have completed the physical implementation, you will be talking about the parasitics. Okay, so Tempest helps you in timing sign off, Voltus helps you in power sign off, and Quantus will help you in extracting the parasitics and analyzing those parasitics, analyzing uh, or to check the impact of those parasitic components on your design. Okay, and Pegasus will help you in physical sign off. Okay, to analyze all those aspects or design rule check layers versus schematic. Okay, any constraints imposed on that. Okay, and if anything is there, they can be checked out. And Pegasus is used for physical sign off of your design. Okay. So let us move into the full custom IC design flow. Okay, we have done it already during the STTP2. Okay, anyway, let us have a quick recap, okay, of what is being done during the STTP2. Okay, so first, as we have seen, okay, as per Vidike's session, we'll be working out on the specification, design specification. Once that is done, you'll check out all the parameters on paper, okay, and then capture the circuit on the EDA tools. Okay, so the EDA tool that is going to help you in schematic capture of your design is going to be Virtuoso. Okay, so Virtuoso schematic editor or composer will help you in the design entry. Okay, and then to check its behavior, okay, to check the functional aspects of the circuit, you'll move into the simulation part. Okay, the simulation tool that will help you in doing this is multi-mode simulator, mmsim, and Spectre is the simulation engine which will help you in running the analysis. Okay, once that is done, you will move into the layout part. Virtuoso layout editor will help you in capturing the layout. Okay, and then physical verification to check the design rule compliance, and they also and compare your layout and schematic. You have Ashura or PVS. Ashura is for higher technology nodes, whereas the PVS is for lower technology nodes. Okay, and then we come to RC extraction. Okay, extract the parasitics after you complete your layout. Extract the parasitics and check its impact on your circuit. Okay, what is the impact of those parasitics on timing aspects of the design and power aspects of the design. Okay, once to check the impact of parasitics, you will be rerunning the simulation. Okay, using the Spectre tool, and finally you'll generate the GDS file. Okay, graphical data stream information interchange, and Virtuoso helps you in generating those files. Okay, so let us move into a quick demo session. Okay, and once that is done, we'll be taking you through the semi-custom IC design flow. Sai Krishna will be taking you through that. Okay, so let us move into a quick demo on full custom IC design. Okay, so as we have already seen, okay, I'll first create a workspace for my design. Okay, so workspace in the sense a directory. Okay, so to create the directory, okay, so what we can do is just you can make a right click and go for create folder. Okay, or you can just select open in terminal if you wish to work on the command prompt. Okay, so easier option will be make a right click and go for create folder. Name your design directory. So I'll name it as S.P.I.T. Enter, and now open that folder. Okay, so I'll enter into that folder. Okay, and I'll open a terminal. Okay, I'll open a terminal. Okay, I'll open a terminal. Now what happens is I'll initialize the shell script. Okay, because the operating system, Red Hat Enterprise Linux and Cadence has certain libraries in common. Okay, so they are mapped with the help of a shell script. Okay, so we are initializing the shell script, and now let us source the CSHRC file. Okay, so CSHRC stands for shell script run command. Okay, which has all the which has the location of the tool installation directory. Okay, CSHRC file contains the location of tool installation wherever your tool is installed in the particular machine. Okay, and from where is the license fetched? Okay, so those aspects will be provided in CSHRC file. So I am sourcing that, and I have given the location. Okay, where is my CSHRC file located? Okay, and I have named that file as CSHRC2. Okay, otherwise it will be just CSHRC alone. Okay, I've named it as CSHRC2. Okay, that is why I'm giving it here. Okay, now you'll be getting a welcome screen like this. Okay, so because you have a list of Cadence tools. Okay, among that you have to choose whichever is going to be made use of for a full custom IC design. Okay, or a semi-custom IC design. So for a full custom IC design, I need Virtuoso for schematic capture. Okay, so I'll invoke Virtuoso, and all the commands are case sensitive. Please have that in mind. Okay, so Virtuoso, I'll invoke the tool. Okay, so license is being fetched, verified. Okay, and once those things are done in the background, okay, it will open your tool like this. Okay, so whatever window you are about to see now, okay, still opening. So this is your command interpreter window. Okay, so whatever process you do, whether it is a schematic capture or simulation, okay, so entire log will be available here. Okay, this will record all the happenings, okay, and it will be available. In case if you have any errors or warnings, then you can come back here and check whatever it is. Okay, so I'll open the library manager, okay, by opening the tools and selecting library manager. So you have the predefined libraries over here, okay, and if you select anything, for example, I'm selecting analog lib. So the components available under that particular library can be checked under cell. Okay. And what are the library files available for each and every component, like a spectral file, okay, which will help you in running the simulation, or a layout in case if you are if you have a capacitor in your circuit, okay, you should have the layout view. Only then when you capture it on the layout editor, we having an idea of how it looks like, okay, or whether it can be taken to your design or not. Okay, so for those aspects, you need certain files, background files. Okay, so these things will be available over here. So in the same manner, you are going to create your own library. You'll be creating the cells, and you'll be creating different types of views for your design. Okay, so to create a library, I'll go into file, new, and select library. I'll name the library. For example, I'm going to take you through an inverter design. Okay, so I'll give the name as one underscore inv and select OK. So for attach a technology node, okay, because everything nowadays, whatever design you make, it is technology dependent. Okay, it is dependent on a particular technology node. Otherwise, it is generalized. Okay, it is not. It is free of any library. Okay, technology. Okay, so I'll select the third option, attach to an existing technology library, and select OK. In case if you wish to work on 180 nanometer or 45 nanometer, okay, so what you can do is you can select that particular thing. Okay, so I can go into GPDK 180, okay, and select OK. Fine. Now you can see the library has been created, but as of now you haven't created any cells, right? So to create a cell for this particular library, you have to select it first and then go into file, new, cell view. Give a name for your cell. Okay, so I'll name it as INV_DES inverter design. Okay, select OK so that you get the schematic editor. Okay, now you have to instantiate the components, okay, with which you are going to build a circuit. So I'm going to build the inverter design using the CMOS technology. So I need a PMOS and NMOS transistor. To instantiate that, so I'm going to create and select instance. Okay, so here I'll have to browse the library. Okay, so I have allocated GPDK 180, right? So I'll have to select that, and in that I'll have to choose my NMOS and PMOS transistor. So I'll select my NMOS device first, click on hide and place the device. Same way, already my library is GPDK 180. So instead of NMOS, I'll go for PMOS, click on hide and place the device. Okay, so we have got the NMOS and PMOS transistors, and now include the pins. Okay, so you need the input and output ports, right? So for that, I'll add the pins. I'll go for add pin option or go to create and select pin. Okay, name the pins. For example, A, VDD, VSS. Okay, so these are going to be my input pins, right? Input ports. Okay, you can name multiple pins at the same instance of time, okay, by separating them with spaces. And since they are input pins, the direction has to be input. Click on hide and place them over here. You can also rotate them by using the bind key R. R stands for rotate. Okay, and now we have got all the input pins. Okay, same way I'll include the output pins. So output is going to be Y, and I'll change the direction like this. Change the direction to output. Click on hide and place them. Okay, now you need to connect everything, right? So for that, I need wire. Okay, so go for the bind key W. Okay, go for the bind key W and complete the connections. Okay, using wires. So I'll complete the internal connections first. Okay, between the devices. Okay, so this is done. Fine. So I've created the inverter schematic. Okay, and then if you wish to change the properties of your PMOS and NMOS transistors, you can select that. Select the transistor and go to its property. You can make a right click and go to properties. Okay, you can see properties, right? So select that. You can change your length. You can change the width of the devices. Okay. So for example, if you want the length to be 1 micron, okay, 1 micrometer, and width to be 5 micrometer. For example, okay, this is for example. Width to be 5 micrometer. You can give the length and width over like this, and click on OK. Okay, same way to the PMOS. I'm go into its properties. Length is 1 micrometer. Okay, and width, let me consider 10 micrometer. Okay, so click on OK and check and save. Okay, so you have two save options. Okay, if you go to file, you have 2 to 3 saving options. Okay, save in the sense it just uh, saves the design for that directory. Okay, and if you go for check and save, it will check for any floating nets. Okay, floating nets or unconnected components, unwanted devices. So if any such things are there, it will throw up an error or warning. Okay, and then save your design. So I'll go for check and save. If you go back to your command interpreter window, the last 2 lines, you can check the information. Okay, in case of errors or warnings. Okay, and then now if you wish to create a top level hierarchy for this, what you can do is you can go for create, and then you can go into cell view. From cell view, okay, you can see the library name and from and to views. Select OK. You can decide upon the pin location. Okay, so on the left hand side I'll have the input pin alone. On the right hand side I'll have my output pin alone. On top I'll have my VDD. Okay, and at the bottom I'll have my PSS. Click on OK. So you can see the symbol, default symbol that is created. In case if you wish to change it, okay, like an inverter has a triangle with a bubble in front. If you wish to change it, you can select the inner rectangle and delete it. Use the create line option. Okay, create line option to draw a triangle, and use the create circle option. Okay, you have the drawing tools over here, and make use of create circle option and create a bubble in front. Okay, fine. So you need not worry about whether these nets have to be connected or not. By default, it will be electrically connected with it. Okay, just we are changing the symbolic. That's it. Okay, by default, all the internal connections will be there. Okay, so I'll go for check and save. In the command interpreter window, you can check for any warnings or errors. Okay, so once this is done, you can close it. Now you can create one more schematic. Okay, to build your test bench circuit. Okay, so what you can do is I'll go into library manager. Okay, I'll select the library within which I need the test bench circuit. So I'll select it, and then I'll go for file, new, cell view. Okay, so now I'll add this. Okay, I'm creating a new cell, right? So I'll have to rename it. I'll give a new name. I'll give a new name. So select OK. Instantiate the symbol that you have created. Okay, so for that I'll go for create instance. and select the library. Okay, 1_INV is the library which has your symbol, right? So you can select that. Okay, click on hide and paste your symbol. Okay, that's it. So you can like this you can make use of the inverter or amplifier whatever you have created in some other designs. Okay, you can instantiate that. Okay, and then add an output port. Okay, so I'll go for create and go for pin. Okay, so I'll name the pin as v_out. Okay, and it is going to be an output port, so the direction will be output. Click on hide and I'll place the pin like this. And then I need some sources. Okay, so for input I need a pulse source in case if I'm looking for a pulse source. Okay, so I'll go for create instance and in analog lib. Okay, so in analog lib, okay, I'll have the components that are independent of technologies. Okay, generalized components. So analog lib. So your sources all come under generalized components. So those things are available under analog lib. So I look for V pulse. Okay, and I'll check out its properties. So for example, voltage 1 is going to be 0 volt. So logic 0 and logic 1 for your pulses. Okay, so for example, I'll give voltage 2 as 3 volt. Period, I'll give 2 nano. Okay, delay time, let me take it as 10 nanosecond. Rise time 1 pico, fall time 1 pico. And pulse width, I'll go for 10 nanosecond. So click on hide and I'll place it. Okay, same way, I'll go for create instance and go for a DC voltage source for my VDD. Okay, have the DC voltage as 3 volt, 3 volt. Click on hide and I'll place it over here. And then I need ground terminal, right? So I'll go for create instance and I'll search for ground. Everything, these components are available within the within your analog lib directory. Okay, so I'll have my ground. Now we'll go for connection. Okay, so I'll make use of wires to complete the connections. Okay, so you can make use of both hard as well as soft connections. Okay, that depends on your convenience. But when for soft connections will be helpful. It will make your design look neat. Okay, like this. So you can use labels. Okay, so L is the shortcut for label. Okay, find key for the label. So I'll label the nets. VDD is what you need, and begin. Okay, so because we need to have the labels in both the places, right? So then it will get connected. So VDD once over here and once over here, and then begin. Okay, fine. So this is done. So so this establishes soft connection between the terminals. So I'll check and save the design. Go back to your command interpreter window. So I don't have any errors or warnings. Okay, so now I can go for simulation, right? So I'll go for launch and open my EDE. EDE stands for analog design environment. Okay, so you can go to setup and first make sure of the simulator. So Spectre is your simulator, right? So select OK. Then you can check out your model libraries. Okay, so whatever the technology node you are making use of, okay, it will have a Spectre circuit simulator within that. Okay, it will be provided by the foundry. So you'll have to browse those files. Okay, since I'm working on 180 nanometer technology now, so this is the location of that SES file. Okay, so here you can make sure of the technology node. Okay, and here in this section you can select the processing points. For example, if I'm working on nominal corner, so I'll select NN. Okay, and in case if SES files of 180 nanometer along with 90 nanometer and 45 nanometer or some other technology gets included here by mistake. Okay, or when you're trying to change some of the properties of the design and when you're trying to resimulate it. Okay, so in those cases, the SES files of other technology nodes also get included here. Okay, so in that instance, okay, if you just run the simulation, you throw up a fatal error. Okay, so it is always better to check modern libraries like this. Okay, and enable the SES files to enable the SES files for which you are going, whichever you are making use of currently. Okay, all of the things can be disabled. Okay, so I have enabled or I have only the SES file of 180 nanometer technology node. So once this is enabled here, okay, if you click on that and tick mark again, it will be disabled. Okay, so I'll enable it and select OK. Now you need to choose the analysis types. Okay, so for that, I'll go into analysis and select choose. And if I am trying to run a transient analysis, so I'll enable transient. Stop time, I need to run it till 100 nano. Okay, and then here you can choose your accuracy default. Okay, what can be your accuracy? Uh, uh, how accurate your results might be. So those things are dependent upon the number of timing instances that are considered for analysis. Okay, so if you go for conservative, maximum number of timing instances in your simulation waveform or from your input will be considered. Okay, and when you go for moderate, considerably lesser number of timing instances will be considered. Okay, and for moderate, mostly least number of timing instances will be considered for the analysis. Okay, so for example, let me go into moderate. I'll select OK. Right. And now I'll go into outputs. Okay, I need to select the terminals between which the simulation has to be done. Right. So for that, I'll go into setup. Choose from design, select my input net and select the output net. Okay, select OK, and to run the simulation, what I can do is I can go to simulation, select netlist and run. Okay, so you can see what is happening in the background. This is the log file. Okay, in case if you have any errors or warnings, you can check those things over here. Okay, and you can go back to your command interpreter window and also check it over here. So you can see 0 errors and 0 warnings. Okay, for your design. Right, so these are your waveforms. You can change your waveform properties also. So if you wish to select change the width of the signal or color of a signal, you can select it. Make a right click, go to style, solid. Okay, and you can change the width. Okay, and you can change the color also. Right, in case if you so currently both input and output signals are merged with each other, right? So you can go to graph and select split all strips. Okay, to uh, have the to view your input and output waveform separate. In case if you wish to change the background color, you can select on the transient response, go to graph properties. Okay, select on color and change your background. Okay, okay, so this is about your schematic capture and simulation. Now let us go into the layout part. So you can also save your state. Okay, simulation state. This is your simulation state. So you can go to session and go for save state. You have to save it as a cell view because you have done everything for a cell view, right? So you have to save it as a cell view. You can also change the name here. For example, I name it as inverter and select OK. Right? So now your save the state is saved. So I close it. Okay, and I can close this schematic also, right? So in your library manager, so now you can see within the library that you have created two cells. Okay, and if you select a cell, you can see the type of views available. You have created a schematic and symbol for this cell, and here you have created a schematic and you have created a state. Okay, simulation state, right? So both are. So now I'll open my transistor level design This is one of the methodology of doing a layout. Okay, I'll open a transistor level design. I'm going to launch and select layout Excel. Okay, select OK. And here also you can select OK. These are some of the issues because of packages. Okay, so nothing to worry about it. It is not going to harm your layout. Okay, so this is your layout editor. Okay, purchase all layout editor. Fine. So you can click on F. Okay, F stands for fit to screen. Okay, so whatever you can see is like X and Y axis of a basic graph sheet. Okay, so now I'm going to get the components from the schematic. Okay, so what I'll do is I'll go for connectivity, generate, and select all from source. So what happens? All the components from the schematic gets imported here to the schematic input. So you'll be able to see like this: a PMOS transistor and a MOS transistor. If you go for Shift F, then you can see the terminals of the devices. Okay, so you can see this box, right? So this is your PR bound, placement and routing boundary. And if you zoom in, you can also see the pins. Okay, VDD, okay, VDD, input pin, your output pin, okay, and your VSS pin. Okay, use F to fit to screen. And on the left hand side, you can see the layers. Okay, this is the layer palette. You can see the layers. And V stands for visibility, yes for selectability. Okay, whether you have the option of selecting that particular layer or not. So if it is enabled, you will have the selectivity option. Otherwise, you won't. Right. Okay, so I'll just rearrange my components. Okay, so currently you'll be able to see only the gate. Okay, whatever you can see in the center. Okay, that is your gate terminal. And on either sides you have the source and bulk, so source and drain. Okay, source and drain are interchangeable, right? Okay, source and drain on either sides of the gate, and you don't see the bulk terminal, right? Because when you look at your schematic, okay, you can see four terminals: gate, drain, source, and bulk. Okay, in order to get the bulk in your layout, you can select the particular device. Okay, so I have selected the PMOS transistor. I'll go to its properties. Okay, so here you can see parameter. Okay, in that you can see an option called body type. Okay, so I'll choose integrated. Okay, so there are two options. Let us see how it looks like. Okay, I'll select integrated and click on OK. So now if you zoom into your device, you can see source and bulk are integrated with each other. Okay, so this is your gate, drain, source, and bulk. Okay, same way. And go for an NMOS transistor, go to its properties, and in body type, if you go for detached, okay, and if you zoom it in, you can see that this is your gate, drain, source, and bulk. So you can see both source and bulk are separated from each other. Metallic strip, and oxide layer both are separated from each other, right? Okay, so let us have somewhere around here. Okay, you can also rearrange the components. Okay, and then you can do the connections. Okay, so first let us complete off. So you can also stretch your PR boundary. Okay, so what you can do is you can make use of an option called yes. Okay, yes stands for stretch. Okay, if you click on yes on the keyboard, select your PR boundary, select any one of the PR boundary, and you can expand like this. Okay, so we have the VDD pin over there, right? So I'll select that pin. Okay, you can zoom in as much as possible and place it on the PR boundary. Okay, like this. Now you can pick your PMOS transistor. So it's your choice. Okay, it's up to us to decide upon how to arrange our devices. Okay, like this. You can rearrange like this, or you can make use of any types of placement methodology. Okay, now I can select my input pin and output pin. you can move it at the same time. Okay. Now let me make the connections. Okay. So I'll connect the gate of PMOS and NMOS transistor. Okay. Now if you wish to check whether it is connected or not, yes, it is done. But there is some misalignment, right? So I'll select the PMOS transistor, select the device, then click and drag in order to align them properly. Okay. Now both are aligned with each other. Okay. Next, I'll connect the drain of both the devices together, and they are connected to the output pin. Okay. And then input. Okay. Input pin. We need to connect it to a polysilicon. Okay. That is, a metal pin has to be connected to a polysilicon, which can't be done. Okay. So what we need is we need a wire. Okay. So just imagine that you are trying to connect two pipes. Okay. Two water pipes of different diameter. So you'll be making use of a coupler, right? So like that, wire is going to be a coupler. Okay, so to include a wire, I'll drag to a certain distance. I'll start the connection and then make a right click, go to wire down to and select poly. Okay, so now I have got a poly. This is N1 to poly. Okay, N1 to poly wire. Okay, so I'll place it, just make a left mouse click to place it and then complete the connection. Okay, so like then it looks like this. Okay, and on top, okay, for VDD and VSS, okay, you can have rails. Okay, so to place the rail, what you can do is I can go to place, okay, in that pin placement. Okay, select the pin for which you need the rails. Okay, so I'll select VDD. Okay, so for VDD, it is placed at the top, right? So I'll select top, edge as top, and then click on apply H rail. Okay, similarly, VSS is going to be placed at the bottom, right? So in edge, I'll select bottom, apply a H rail. H rail stands for horizontal rail and V rail for vertical rail. Okay, now you can click on close. Okay, so you can see here. So at the bottom, you have the VSS and on top, you have the VDD. Okay, now you can complete the remaining connections. Okay, so in case of integrated, okay, so you have a combined net, okay, combined path segment. Okay, so I'll go for increase the bank key. Okay, so I'll complete the connection like this. Okay, and same way. Okay, so since it is detached, both has to be connected separately. So once for the source of NMOS transistor and once for the bulk of NMOS transistor. Okay, fine. So save your design. Okay, save your design by using the save option. Now we can go for the physical verification process. So I'll go into Ashira and select technology. Okay, browse the library file. Okay, because Virtuoso understands your layout. Okay, and Ashira doesn't understand your layout because that is a different tool which understands only the design rules. Okay, or the netlist file. Okay, so I'll browse a library file which helps you in mapping these things. Okay, so I'll go for browse. Okay, and I'll go into Foundry. Okay, so I'll go into Foundry, which is available in Home, CAD, and here I can see Foundry. Okay, I'm working on an analog design flow. I'm using 180 nanometer technology. Here I have Ashira underscore tech.loop. Okay, so this will be the library file that helps me in running through the physical verification. Okay, so now select OK. Again, I'll go back to Ashira and select run DRC. I'll give a run name. Okay, any name, it can be any name. So I'll mention it as INT. Here I can select technology mode. Okay, so click on the drop down and select GPDK 180. So once you select it, automatically the DRC rule file gets imported here. Select OK to run the DRC. Okay, click on watch log file to check what is happening in background. And here, if you select yes, you can check out the result. Okay, so now DRC error is found. Okay, so next is LBS. I'll go to Ashura again. select run LBS, give a run name. Okay, so I'll name it as INV_LBS. Okay, so you can browse the technology library. Okay, and click on OK, right? So it is asking whether it has to be saved or not. Your design has to be saved or not. So just select yes and click on watch log file to see what is happening in background. Okay, so your layout and schematic, okay, both are compared with each other. Okay, and these are the results. Okay, so you don't have any mismatches. Okay, and you don't have any net mismatches, you don't have a device mismatch or pin mismatch, etc. Okay, so if you select yes, you can see the overall report. Okay, so you can see like this schematic and layout match with each other. So we are closing it now. Okay, now the physical verification, sorry, parasitic extraction. So I'll go to Ashura, run contest QRC. Okay, so you wish to see an extracted view of your layout, right? So I'll select the output as extracted view. Okay, so I'll go to the top again and I'll go into extraction. Okay, so here I'll mention what are to be extracted, whether I need only the resistors alone or I need both resistors and capacitors. So I need resistors and capacitors, right? So I'll select RC, okay, in reference with the VSS. Okay, RC, resistors and capacitors in reference to the ground VSS. Okay, now select OK. And if you go back to watch log file, you can see what is happening in background. Okay, right. So the extraction is completed and the output is available within this library under this particular cell, and it is saved as AV_extract. So go for close. Okay, and in the library manager you can see it. Okay, under that particular cell. So if you make a double click, okay, so you can see. If you select yes, you can see the extracted view of your layout. So you can zoom in further. Okay, use your mouse scroller. So you can see P resistor, right? So similarly, you can see some P capacitors also. These are also P resistors. Okay. So here you can see a P capacitor. Okay, so if you click on Shift F, you can check out what is the value of the particular capacitance. Okay, and here also you can see the value of that particular resistor. Okay, so we have to import this, rerun the simulation to check its impact. Okay, so how to do that is, so I'll close everything. Okay, so I'll select the test bin circuit and its schematic. I go to file and create a circuit with the type as config. Okay, so it is going to be a configuration view. Okay, and select OK. So here you can see a new configuration window. So you have to browse the simulator here. Okay, Spectre is the simulation engine, right? So go to use template and select the template name. It's a template name. Spectre has to be the simulator and select OK. Okay, so select the top cell view. Okay, so the top cell view is a schematic, right? So sorry, schematic is going to be your top cell view and select OK. And now you can see table view and tree view, right? So select tree view, and that you can see the instance, okay, that is available in your circuit. Okay, so if you expand this, you can see only the PMOS and NMOS transistor along with the sources. Okay, your pulse source and DC voltage source, right? So I'll select that instance, make a right click, go for set instance view and select AV_extracted. Okay, so all the parasitics get imported here now. Okay, so save this configuration. Okay, so go for view and select update. Okay, and now you can open. Okay, just below top cell you can see open. So it should bring back your test bench circuit. Okay, and if you peep down, okay, you can see the extracted view. Okay, you can just cross verify whether all the parasitics have been imported. Okay, so now you have to rerun the simulation. So for that, I'm going to launch and select ADEL, right? Load the state. Okay, you have already saved the simulation state, right? So I'm going to session and select load state. It was saved as a cell view, so select cell view and select OK, right? So whatever analysis you have chosen and whatever input and output nets you have chosen, everything has been imported. To rerun the simulation, I go to simulation and select network standard. Okay, so this is how you run the pre-layout, post-layout simulation. Okay, and then you do the layout and physical verification process. Now the final step of generating the GDS file. Okay, so to generate the GDS file, what we can do is I'll close all the remaining things. I'll go into Virtuoso tab. Okay, that is your command interpreter window. I'll go into File. Okay, Export. Okay, and under Export, I'll select Stream. Okay, so in your stream mode file, okay, the GDS file is also called as stream mode file. So what I'll do is I'll go for library, and you can see here. Okay, so the view is layout. Okay, so what you'll have to do, you have to go to the library, select the cell which has the layout. Okay, so go for browse, select the library and select the cell which has the layout. Okay, and select OK. So you get the stream of file name also. If you wish to change it, you can change it, but the extension has to be .gds. Okay, now select the technology library. Okay, you were working on JPDK 180, right? So select the technology library and go for translate. Okay, so let's move on. Process is done. So you can have a view at the log file. Okay, you cannot view the stream out file. Okay, because it is a binary file. So everything will be available within the directory that you had created at the beginning. Okay, so you can see the GDS file. Okay, so it will be like imd underscore des dot gds. Okay, which you have already seen. Okay, during the stream out file name. Okay, so here it is. Okay, dot gds. We try to open it because this is the unsupported format. Okay, you have a separate extraction tool. Okay, so this is about the overview of a full custom IC design flow. Okay, in case if you have any doubts, you can let me know. So the tools that are used in front end for full custom IC design flow will be Virtuoso for schematic capture, okay, and S.P.I.T for simulation, functional simulation. And at the back end for designing your layout, okay, uh, Virtuoso layout editor for designing the layout, and for physical verification is Ashura, okay, Ashura or PBS. And for post layout simulation, again, you make use of S.P.I.T. Okay, and for generating a GDS, again, you come back to Virtuoso. So these are the tools for physical for tools in front end as well as back end for full custom IC design, analog IC design. Okay. So now Sai Krishna will be taking you through the semi-custom IC design flow. Okay. So over to you, Sai. So any doubts still now on full custom IC design flow or the tools involved in full custom IC design flow? Any doubts, participants?
No.
Okay, sir, fine. So Sai can take over. Sai Krishna, are you online? Or Saraswati?
Yes, sir, I'm there 1 minute, sir.
Yeah.
Naveen, I'll have to do the access right.
Yes, sir. Saraswati has to be the presenter.
Okay.
Yes, sir.
Sir, I think Sai Krishna is there. You can make him as a presenter.
Done.
Sir, I'm audible.
You are audible, Sai. You are audible.
Couple of
Hello.
Hello. Yes, sir.
Sai Krishna, are you there? He has not shared the screen. Share.
yes, sir.
Just a second, sir.
It's connecting, sir. Just a second.
Acha, acha. Okay. See, pin drop silence. No, we don't come to know what is happening.
Yes, sir. Yes, sir. Just a second, sir. Just a second.
Yeah, yeah.
Navin, sir, I mean, there is a
Yeah, I'm taking care of it. Sai, any issues? Hello. Sai?
Rathod, sir, could you please make Saraswati the presenter? Having issue with sharing.
Okay, okay. I'll do. Okay, done.
Saraswati, you are the presenter now.
I just open up PPT one minute. Yeah, is it visible, sir?
Yes, yes.
Okay.
Visible.
Okay. Yeah.
Please, Saraswati. So,
Okay, fine.
well, first of all, apologies for those technical issues, everyone. So, Krishna from Entuple, and I'll be taking the session forward. So, Naveen sir already explained everything about custom IC design flow.
Sai sir, little louder, little louder.
Is it okay now, sir?
Now okay.
Okay. So as Naveen sir already explained everything about full custom IC design flow, let me take up its counterpart, the semi-custom IC design flow. Next. Saraswati, next. So in the first session today, we let's just have a look on the complete semi-custom IC design flow, which is also called as application-specific IC design flow, SIC. And we'll also have a little detailed look into the front end part of it. And then we'll be continuing with the synthesis and pre-layout timing analysis for today. Next. So as the name itself indicates, and as the name itself indicates, application specific IC design is something you build where you build chips for a particular purpose. So in in your as Naveen sir showed in your full custom IC design it, verifying STA and been dealing with the physical aspects of it in the layout and then sending it for fabrication in the form of 3D SPI. So here in a semi-custom flow, we are not going to deal with circuits. First of all, why do you need a semi-custom or ASIC design flow? Why are we not dealing with the circuits? What is the importance of custom IC design flow in the industry? So to talk about these, in your full custom IC design flow, you deal with your transistor level circuit designs. So as every one of you know, with the uh, day-to-day demands in the electronic gadgets, they are becoming more and more complex, and we are actually developing miniaturized circuits and handling complex functionalities. For example, if you take your mobile phone has a camera, it has a storage, memory storage, it has a calendar, it has a calculator. So it is a simple chip that has several devices integrated into it. So when you're dealing with such complex functionality, and if you want to realize them or if you want to construct them in the form of a transistor level circuit, it is a it is a huge backbending process, and also it would take you probably years of time. And in the market, if you have to sustain the competition, you will have to bring out your chip at most in let's say 6 months or a maximum of 1 year. So if you are using full custom IC design flow to deal with that are intended to carry two large functionalities, you cannot use so an alternative, we uh, we use semi-custom IC design flow. So to keep it simple at the top level, your semi-custom IC design flow makes use of the sub-designs that you have generated earlier from your transistor level circuits. Something like your inverters, buffers, NOR gate, or your adders, multipliers, etc. So all these type of sub designs are actually built earlier and are directly used into your semi-custom IC design flow. So that is how you are not you are no longer dealing with transistor level circuits, but you are dealing with the so-called gate level or standard cell level circuit. So what are these gates? What are standard cells? We shall look into each one of as we go further. Next slide. So the flowchart is your ASIC design flow. So before we actually look into each page, let me just make it more simple for you. No matter whether you're dealing with custom IC or semi-custom IC, you basically follow a six-step procedure. Six-step procedure. So the first step of it is you can note it. The first step is realizing the specification for your design. That you will try to understand what is it exactly that you need. Now, for example, if you talk about a simple inverter, you will first specify that uh, this particular inverter should perform so and so function. It could be in terms of Boolean expression or in terms of truth table or for that matter in any form. We'll first talk about the working of it, and then you talk about what is the maximum power that it can consume or what is the response time it has to carry or for a certain given input uh, you know when a certain input is given, how quick is the output popping up. So you define all such factors like these. So all these factors can broadly classified into two things: your functionality and your physical aspects. So in step one, once you realize your specifications, you first build functionality. So how we build it depends on the flow. But uh, am I is my voice not clear yet?
At times it is breaking, Sai.
Breaking and a little louder also. It is very low.
Is it okay now, sir?
Yeah, it's
Ah,
okay.
yeah. When you say this, that time it is okay, but immediately again it goes. Okay.
Okay, sir. I'll try to maintain this.
Ah, that's
Uh,
it. That's it. Okay.
yeah, just cut me in between if the voice goes very low, sir. Okay. Yeah. So as I was saying, uh, in VLSI, when you want to develop a design or a chip, you follow a six-step procedure where the first step would be realizing your specifications. What is it exactly that you need? So under this specification, we talk about two things. The first one is your functionality part. How exactly does your design work? For a given input, what is the expected output? And the second part is relating to your physical aspects, such as the area occupied by your design, or the maximum power dissipation, or the response time, etc. So once you realize all of these, once you're clear with all of these, you first build your functionality. So how do you build it? Depends on the flow. It could so as you have seen earlier in your full custom IC design flow, you are doing it in the form of a schematic capture. So there you are building a circuit which for a given input gives you your expected output. So once you do that, always please to keep this in mind that VLSI is a billion-dollar industry, and every chip being manufactured has to be cross-checked for every aspect uh, before you proceed. So whatever functionality you have built, you will have to first verify that also. So for that, you force a certain input signals onto your design and check its corresponding outputs with respect to time. So that is nothing but your transient analysis or your functional simulation. So be it full custom or semi-custom, once you have built your functionality, you are going to simulate it with a stream of input signals. And then once your functionality is verified, we then move on to your physical aspects. And there's a certain process called physical design. And to cross check that all your physical design is fabricatable, we go to physical verification, where you perform DRC, design rule check, and LVS, layout versus schematic. So once your physical design is also done and verified, you go for the sixth and last step, creating a GDSII file and taping out your design. So this is what happens both in full custom flow or semi-custom flow. Now when you just overlap these 6 steps onto your semi-custom IC design, the first step, specification, corresponds to the same here, and the second step, building your functionality. So in your full custom, as I said, you're building your functionality using schematic capture, but here you're going to do it using RTL coding, register transfer level coding. So here we use the HDLs, hardware description languages. To those who are new to it, HDLs are the programming languages that can be used to describe a design and its behavior and make the physical implementation easier. So we basically use two programming languages. One is Verilog and the other one is VHDL. So using either of these two languages, you write down a program. You write a program whose logic is expected to be in line with the functionality specified. So once you write your program, you also write a test bench. A test bench is another type of program which forces a series of inputs onto your design. So you write a RTL code and a RTL test bench, and using both of them, you simulate your design. So once you simulate your design, you'll check for a given input, what is the output you're getting, and if it is in line with your specification, that means the logic you have written is proper. For an example, if you are writing a RTL code for a simple inverter, let's say, when your input is logic 1, your output should be logic 0. And when your input is logic 0, the output should be 1. So even your waveforms or the values after your simulation should represent the same. So once that is done, you can proceed to physical design. Here in semi-custom IC flow, Physical design is a 5-stage process. It starts with floor plan and continues with power plan, placement, CTS, and routing. Power plan, floor plan, power plan, placement, CTS, and routing. After your functional simulation, as per the 6-step procedure, we go with physical design. But here there's a small catch. Earlier in your full custom flow, you were uh, capturing schematics in the form of circuits. I mean, using some transistors. So that means you have a physical reference there, and that is why, based on your schematic, you were able to directly move on to layout, the physical design part. But here we don't have any such real references. The functionality that you have built here is in the form of virtual logic, in the form of a high level program. So you cannot directly go on to physical design using that high level programming. So that is why, to bridge this gap between the functionality and the physical implementation, the PD, physical design, you take an extra step, synthesis. So I believe every one of you are aware that the word synthesis in our day-to-day English, synthesis actually means conversion. So if you remember, photosynthesis. Photosynthesis is converting photo light to some chemical form, right? So synthesis basically refers to conversion. It does not mean generating something uh, or anything of that sort. You're not changing anything here. You're just converting forms. Okay. So as a part of synthesis, you convert your RTL code. That means your high level programming logic into a gate level circuit. I repeat, in synthesis, you convert your RTL high level RTL code into a gate level circuit. Okay. So gates are nothing but the sub designs that you have already generated using your full custom IC design flow. Okay. So those designs can be, I mean, the functional and physical aspects of those designs are are compiled into certain files called library files. We shall see what are they and what do they contain in the later stages. But all those library files contain the functional and physical information of your sub-designs. So using those library files, you convert your RTL code into your gate level circuit. So as I earlier said, semi-custom design basically deals with high complex designs. So when the design complexity is so high and the number of gates or the number of components in your design are too high, then obviously your fabrication might also become a little complicated, which could lead to some unnecessary faults. You know, something like unnecessary short between two wires, or any wire being improperly routed, or anything as such. So if that happens, a chip after it being fabricated will be dysfunctional. It'll just be a mere waste. So that's why after synthesis, we go for DFT, which stands for Design for Testability, where we intentionally induce certain faults into our gate level circuit and test it. Like let's say, for example, consider a simple AND gate. Okay, consider a simple AND gate, A and D AND gate. So it has two inputs and one output. right? Assume that one of the inputs is shorted to ground. Assume one of the inputs is shorted to ground. So that means the possible inputs are 0, 0 and 0, 1. In either case, your output should be only 0, a constant low. But during, but in case if your output is turning out to be a high value, a logic 1, that means your design is not in line with your functional specification. I hope it's clear. I'm just trying to give you a simplified idea of what DFT is. So one of the input being shorted with ground could be an issue during your fabrication. So in such case, with the available inputs, you should still get an output in line with your specification. So that is what is checked under your DFT. So once you are done with RTL coding, functional simulation, synthesis, and DFT, you then go to physical design, execute all the 5-stage process, and then you also check for timing, area, and power. Timing, area, and power are the 3 crucial factors related to your design that you will be taking care in your physical design. And once that is done, you uh, you perform physical verification and then tape out your design using a GDS II file. So here GDS II stands for Graphical Data Stream for Information Interchange. It is not Roman number 2, it's a misconception. It is II, and as the name indicates, the file carries all the graphical data streamed out or lined up for it to be interchanged between your fabrication unit and your EDA tools. So here the EDA tools that you would be using for semi-custom flow from Cadence are Genus for synthesis, and then Tempest for timing simulation, Modus for DFT, Innovus for physical design, Voltus for power analysis, PVS for physical verification. Yeah, so these are the basic tools that you use, and you also have certain tools like Liberate, which is used to generate the libraries from your subdesigns from analog flow, or you also have Conformal, which deals with logic equivalence check. Uh, excuse me. Yes, so you have Conformal, which deals with logic equivalence check. And just to give you an idea, LEC is a process of checking whether the design from 2 different stages. That means let's say your RTL code and the gate level circuit after synthesis, are both of them same as per the logic or not, or the gate level circuit after your synthesis and the one after routing, are both of them carrying the same logic or not. To check that, we perform LEC in the conformal tool. Okay, next slide. So as I've mentioned earlier, the front end part deals with the architectural design, the RTL coding, and its verification, whereas the back end starts with your synthesis and STA. So architecture is nothing but once you realize what exactly is your chip design specification, you build an architecture. That means you build a technical specification and you try to understand what are all the modules present in order to achieve the complete the overall functionality. For example, if you take your mobile phone, you need one module for, or let us be more precise. If you take your processor, if you're building a processor chip, you need one module that performs ALU operations, arithmetic and logic unit. You need one block that deals with the memory. You need one block that deals with inputs and outputs. So like this, each and every um, each and every block is defined and an architecture is built for it. And then every block is individually built starting with your RTL code. So as you can see, once you are done with your RTL coding, you also write a test bench for it and simulate it to check the waveforms. So using Cadence tools, you can either check your functionality in the form of waveforms, or you can also use uh, the console of your Linux environment to directly look at the values in numbers. Okay. So once that is done, you go for synthesis and also perform timing analysis. Next slide. So I hope I gave you an overview of what you're going to do in the next today and tomorrow, what we are going to deal with. So I've tried to keep it simple and just help you understand what is what. But let's look at each of the step in the ASIC design flow. Uh, what is it? Why we do it? And how we do it. Let us understand all these three questions at each and every stage. So starting with the specification and the architecture, the chip architecture. So imagine yourself to be a designer and you want to build a chip. So the first thing that you do is declare what is the functionality or the application. Do you want to use it, say for some medical purpose? Is it going into a medical instrument, or is it for a satellite, or is it for a something like your mobile phone or any electronic gadget, or is it for any general purpose application or anything as such? So first you decide that, and depending on the application, you decide how much area must your chip be taking up, what is the maximum or minimum power that it can dissipate. If you observe, let me take the example of medical instruments. Your medical instruments, most of them at the chip level take or sorry, most of the medical instruments dissipate power in less than nanowatt range. Whereas when you come to your mobile phones, they are relatively higher. Or if you like that, depending on application, your power requirements keep on changing. And also, it's the same with your performance. Here, performance actually means your response time. When you give an input, how fast are you getting your output? Okay. Um, so based on these factors, you first declare them and also try to give a framework for your chip. So that is your chip architecture. Next slide. So in this process, you also define what are the subblocks of your chip and you try to deal with them individually. So here, if you see, if you take the example of an application processor, you have certain submodules like a USB port, your GPS system, Wi-Fi or Bluetooth, your wireless connectivity system, or you have some audio system, you have flash drives, speakers, etc. So all of these subblocks are uh, could be an integral part of your processor, or they could be partially partially connected to some system directly in your processor. So that is because we cannot build the whole processor single-handedly, or and also it becomes way too complex. We first break it down into pieces, subblocks, and then each subblock is taken through the complete ASIC design flow first. So for this subblock 1, what is the specification? How do you write its RTL code? How are you verify it, and then perform synthesis, then timing analysis, then DFT, LAC, and then physical design, physical verification, and then only when everything is qualified, you take that uh, subblock design and integrate it back into your chip level design. So that means here you're talking about two different hierarchies. One is at your chip level or your top level block, and the other one is your sub block. Okay, next. So when you are taking a single sub block and you started with your RTL coding, uh, one as I said, you can use either Verilog or VHDL, but the most preferred language is your Verilog, because Verilog is such a hardware easy to write a program, to understand it or debug it, and also it has certain advantages like it has flexible modeling types. That means Verilog provides you uh, a certain set of modeling types, which shall be discussed in the subsequent slides. So, and you can also use top to down or bottom up methodology. That means if you are starting with your chip and then moving down into your subblocks, that is your, and then further down into your basic cells, that is your top down methodology. Instead, if you are starting with the basic cells, combining them into subblocks and then integrating it further into a chip, that is a bottom up methodology. So whichever methodology you take, whichever method you take, you can use Verilog in both the aspects. However, there are certain disadvantages for Verilog also, and one of the most prominent of it is its lesser support for asynchronous signals. So when your design is based on synchronous signals, Verilog gives you the best results. Whereas if it is for asynchronous, it may or may not be. It depends on the designer. Next slide. So as I said, you basically have three types of Verilog modeling here. The first one is data flow, which is dependent on your Boolean expressions. So when you take data flow type of Verilog coding, you directly write down Boolean expressions in order to move your logic forward. Whereas when you come to structural uses predefined modules or predefined Verilog codes. So here, the example that you see here is for a adder. So here we already defined what a full adder is. I hope all of you, I hope there are no students from second year or so. So, um, so full adder is already defined, and that logic or that full adder program is being used as a primitive here to to call in your inputs, process them, and give the output back. So that is your structural. So it is in the structural model or gate level modeling, where you can also use your basic logic gates, your inverter, buffer, and NAND, NOR, XOR, XNOR, everything directly in your program. And then the third and the most preferred coding style is your behavioral model, which is the most efficient when you are particularly using synchronous signals. So as the name itself indicates, behavioral model. That means you are writing a program in such a way that it, uh, that you are following the behavior, you're following the response of your intended design. That means when you give a stimuli externally, your design will respond to it with a output. So in a given situation, how do you behave or how do you respond is your behavior. Similarly, for a given stimuli, what is the output you get is the behavior of your design. So here we follow that behavior. So if you take a simple inverter, when you give a input 0, you need to get a output 1. So that is the behavior of your inverter. So based on that, we write the code. So you can always write your Verilog coding in any of these three formats, depending on how you want to do it. Okay, slide. So, um, so as I said, behavioral consists sequential programming. That means all your instructions are sequential in nature. Whereas data flow is concurrent, all of them happen at the same time with respect to a reference, and structural because you are directly using a predefined uh, module. It depends on the interconnects, and behavioral follows the behavior, and data flow follows the algorithm. It's a the kind of algorithm that using which you drive it, and structural is based upon your RTL abstraction or the gate abstraction, right? Okay, next. So here, using any one of those modules, uh, just click next. So what? Sorry. So once you write down your RTL code based on any particular style of your RTL coding, you need to test it using a test bench. That means your RTL code here under verification is called design under test DUT. So onto this DUT, you force a certain input, certain stimulus. You force a certain stimulus and then you see what is the output you're getting. So as per your specifications, you already have a prediction that for a certain input, this should be the output. And when you actually test it using cadence tools, you will get a certain waveform or a certain value. Now, when only when these both of these, your prediction as well as the actual value after simulation are the same, be precise, exactly the same, you can go ahead and proceed with synthesis. But if your captured values and your predicted values are not the same or they have a certain deviation, that means there is some fault or some problem with your program. So that is why your functional verification is very important. If your functionality itself is not proper, then it makes no sense to go ahead, convert it into a gate level circuit in synthesis, and then perform physical implementation. Okay, so here your DUT, which is your RTL program containing the logic, and your test bench, which contains your inputs. Both of them are connected using a process called instantiation. That means you call your RTL code or your RTL main module into test bench, that is called instantiation, and force all your stimulus, your inputs onto it, and see what the output is. Next. So that basically sums up your front end part. Um, your architecture, your chip architecture, the top level, and then your block level architecture, and based on the specifications given for every block, you write down a RTL code in either data flow or structural or behavioral model. And after that, once you write your RTL code, you also write its test bench, and then making your RTL code your DUT, design under test. You force the values from your test bench onto the main logic and compare the captured values with the predicted value. So only if both of them are the same, you can go ahead for synthesis. Else, you will have to go back, check your RTL code, debug it, and then resimulate your design. So for this simulation process, the tool that you use is Cadence. So Cadence Incisive has certain submodules or certain features where let me just quickly give you a glimpse of it. The first one is NC Launch, which is the GUI operating format. So here the simulation is done in 3 stages. First one is compilation, second one is elaboration, and third one is simulation. So compilation means converting your high level programming language into your machine level language. And then elaboration means, as the name indicates, getting into details. That means your tool will try to understand from your code what are your inputs, what are your outputs, what are the blocks that you have defined, and how are they interconnected. So all that information the tool understands during your elaboration stage. And then finally, in your simulation stage, all the input values from your test bench are forced and your outputs are captured. So in NC Launch, all of this happens in your GUI format, visual format. Whereas if you want to do the same your terminal or on your console, you can use NC Verilog first, where compilation and elaboration will be done. And then if you want to then switch to waveform, you can use NC. So the NC Verilog and NC Sim go as a set. And then if you want to perform compilation and elaboration separately, you can use NC Vlog and NC Elab. All of this is for Verilog. If you're using a VHDL program, then for compilation, you'll use NC VHDL and then NC Elab again for elaboration, and then NC Sim for simulation. Okay, so compilation, elaboration, simulation are the 3 stages, and depending on your convenience, use it. So that is all about the front end part. Any questions till this point? Anything you want me to repeat or anything you did not understand from anyone? Okay. Rathod sir, do you want to go for a break or can I continue? Rathod sir? Rathod sir, are you there? Okay, fine, Aaron, let's take a short break. about 10 minutes. Please come back in. Right now, I think it's 12:05 or so. Please come back by 12:50. Once you come back, we shall talk about synthesis and timing analysis, and then we shall proceed with
Hello.
Rathod sir. Hello.
Yeah, Sai Krishna.
Yes, sir. Sir, we'll take a 10-minute break.
Yeah, there is some issue in my mic. Just a minute. Yeah. Hello.
What, sir?
No. My connection got a little loose, so I was not able to hear what is happening. My connection somewhere was loose. Okay. You're given
Oh,
10 minutes break, na?
yes, sir. 10 minutes break.
Yeah.
Is that fine, or do you want to extend it?
No, it's okay. It's okay. Fine. 10 minutes break.
Okay.
No issues. Yeah.
Right, sir. 10 minutes.
Yeah.
Sir, can you make me the presenter once? Invite.
Achha, you're present. Okay. Just a minute.
Saraswati is a presenter right now. I just
Uh-huh.
stay in the
Okay. Yeah. Done. You want to try?
Yes, sir. Make me the
Okay.
presenter once. I'll try sharing
Yeah, I did. Already did.
it.
Yeah. Okay.
It's not yet enabled, so share option. So please make Entuple underscore Sai Krishna the presenter. Rathod sir.
Yes. I did that. I have given
Yes,
you
I just got it.
Yeah, I have given. Multiple sizes.
Yes, sir. Got it. Right. Rathod sir.
Yes, you can start.
Sir, I have rejoined. Could you please make me the
Oh,
presenter once
oh,
again?
oh, oh. Then Entuple underscore Sai Krishna. Na?
Yes, sir.
Yeah.
Yes, sir. Got it. We'll just wait for another couple of minutes, sir, and then
But you try your sharing, or see you are going to share now, right?
yes, sir, I'm checking.
Check it out. Sharing option.
Sir,
Yes.
sir, I don't know why I'm unable to share my screen. You
So
can
again, Saraswati.
continue. Yes, sir, you can continue making Saraswati the presenter, and we'll start. Saraswati,
Start.
please share your screen. Saraswati. Saraswati, you there? Uh, I hope everyone are back. So let's continue with where we left off. So we have already looked into. I hope um, I hope I'm clear and audible to everyone. Anyone please
Yes,
confirm?
yes. Yeah.
Okay. Okay, sir. Thank you. Uh, so as we have already discussed, we start with a chip specification, a chip architecture, and then we divide it into subblocks, and each subblock is taken through the complete ASIC design flow. So here we have taken a simple example of a FIFO system, the first in first out system, and to show you how an RTL code is built, the test bench, the simulation part, and the synthesis is done. Okay. So next slide, please. So this FIFO that we are dealing with has a depth of 8 bits and a length of 32 bits. So it's a 32 by 8 bit FIFO system, which is a memory cluster to read or write data, to read out or write in data based on a certain control signals. So here to the left, you can see what are the signals or inputs and outputs involved in the operation of this FIFO design. So this FIFO meant to be re- um, is meant to be taking in and saving data, or when requested, give out a set of data to the user based on the write enable or read enable. So when write enable is high, then data is written into the FIFO system, and when read enable is high, the data is read out. Okay. And what is that data that is coming in is shown in data pen, and whatever data is being read out outside the system is an output data out. So during this process, if all the 32-byte memory cluster cells are filled, and if they are full, a flag is raised, full flag named full is raised, and the um, yeah, it is raised, and on the contrary, when there is no data in the FIFO system, the empty flag is raised. And how many number of read and how many number of write items are made are also recorded. So this is a simple insight into the FIFO that we intend to build it. So using writing a RTL code, particularly a Verilog code for this FIFO, requires first uh, understanding of what are the inputs and what are the outputs first, and then how are they interconnected. So as I just now told, you first reset everything. I mean, first you declare your inputs and outputs, then reset. You make the reset high just to make sure everything is clear in the system, and then you put your enable high, and then depending on your read or write enable being high or low, reading or writing is done. So after a certain after a certain set of attempts, including both read and write, your empty and full flag will have a status, and your FIFO will have one or more or maybe even zero data sets. So this functionality is to be realized in terms of RT. So whatever in this whole process, if you take it a little more detailed, you will see conditions everywhere. You'll see conditions everywhere. That means first, if you start with reset, if it is high, everything must be zero. No process is being done. If not, that means in the other case, you check for your enable signal. Now, enable has again two conditions. The 1 bit, so two conditions. If it is zero, nothing happens. If it is one, then which one is right, your read enable or write enable. So like this, you check every condition step by step and write your logic in such a way that um, it takes care of all the possible input combinations for every input, and you get a corresponding expected output. Okay. So you write a RTL code accordingly, you write a test bench, and then you simulate it. In case your predicted output is exactly the same as your simulator output, then next slide. Then you go with next slide, synthesis. So what is synthesis? As I told you, it is a process of converting a HDL design into a gate level circuit. That means you are converting a virtual logic into real uh, circuit level components. Okay, so just like your simulation, even synthesis has three stages, and those three stages are translation, mapping, and optimization. Okay, please keep this in mind. In all of your, please keep this in mind in all of your semi-custom IC design flow. Each stage is critical in realizing either your functionality and your physical aspects. But synthesis is the only stage which handles both of them, both your functionality of the design as well as the physical aspects of your design. So synthesis is to be understood in detail and has to be operated carefully if you want the maximum results. Here I'm not talking with respect to the tool, but I'm talking with respect to the design process. Okay, so next slide. So this is a pictorial form of all the three stages. So initially, all your high level language is converted into your machine level language in the translation stage. And after that, your elaboration, sorry, after that, your mapping happens where every instruction or every block of your RTL code is mapped to the sub-designs that are present in your library files. And then the cell count is brought to as low as possible during your optimization stage. So first translation, mapping, and optimization. All the three together will give you synthesis, your synthesis output. So what are those outputs? Nothing but your gate level circuit to be the primary one. Next. So which files do you actually need in order to perform your synthesis? So you have three basic inputs, out of which two are mandatory. The first mandate input is your RTL code. It could be a Verilog code with an extension of .v, the file name with an extension of .v, or it could be a VHDL code with a file name and extension of .vhd or VHDL. Okay, so your RTL code is the first input that is to be read into the EDA tool performing synthesis. Now this code contains the primary logic. Please do remember that you're not going to consider your test bench here, but only the primary logic. Okay, synthesis has nothing to do with verification. It is a part of your design process. RTL coding is design, functional simulation is verification. And now you again come back to design and synthesis. And the next stages, timing simulation and DFT are your verification part again. So like this, alternatively, we deal with it. So that's why here you take only the main code and then you also read your library files. So as I earlier said, library files are nothing but they are the compilation of the functional and physical information of the subdesigns. Something like your basic logic gates or adders, subtractors, multiplexers, demultiplexers, code encoders, decoders, etc. So here under whenever I say libraries, I'm basically referring to two types of file formats. Two types of file formats. The first one is .lib. .lib means liberty file. Liberty file contains the functional information of all the subdesigns captured in the form of timing models. I repeat, .lib, which is liberty file, contains all the functionality information of the subdesigns in the form of timing models. It also contains certain other basic information related to the design, which we'll look in detail. And then the second file format is .lef. So .lef stands for Library Exchange Format, which contains the physical information. That means now in your full custom IC design flow, you have seen that you're actually drawing a layout for a certain design, and then you're taping out the layout alone, right? All your inputs, outputs, and the functionality is enclosed in the form of the connections. So it is your connections that drive an input data, and your devices manipulate it and give you an output, right? So in that layout, what are the pins you have? What is its interconnectivity? Oh, sorry, what is its connectivity and everything, and including the switching of the signals. All of this information is captured in .lib. Now the other side of the coin, which metals are being used or which physical materials are being used. Uh, what are the dimensions of each of the physical layer? It could be polysilicon, metal 1, 2, 3, and so on, or even the oxides and diffusions. If you have vias, what are the dimensions of those vias? I mean the minimum dimensions that are to be maintained. So all such physical information is stored in lefts. So your lib and left together will give you or will help you to reconstruct your standard cell completely. Okay. So however, uh, during logical synthesis, that means converting your RTL logic into gate level circuit. For that case, you will be considering only .lib as an input. You are not going to take .lef. It's only .lib. So RTL code and .lib are the two mandatory inputs that are to be given for your synthesis to happen. Now, along with this, there is another input, SDC, which stands for Synopsis Design Constraints. Synopsis was the first one to introduce this file format, and that is why it is called so. So SDC basically contains a certain set of regulations that you want to impose onto your design for better performance. Okay. So once these three inputs are given and translation, mapping, and optimization is done, in simple, your synthesis is done. The outputs you get is a gate level netlist, which encloses all the connectivity of your standard cells. And then you get another SDC and along with log file and reports. So you may ask me, we are giving SDC as an input and again taking it as an output. What is the difference? The difference is that the input SDC comes at your chip level. Your input SDC comes at the chip level. After synthesis, the output SDC is for your block. I hope it's clear. The input SDC for synthesis is for the chip, the SDC that you have designed for the chip. So based on that, all your blocks are converted to gate level circuits, gate level blocks, and then whatever SDC you get is the list of the same constraints applied, but uh, i- but effective for individual pins and blocks. And the reports that you get are primarily your area report, power report, and time report. Hope it's clear till this point. So slide. Let's see what each file can visually. So the first one is your RTL code. As I said, you can either write a Verilog code or VHDL code. So accordingly, you will be putting the file name. Sorry, accordingly you'll be taking the extensions for your file name. So a couple of important points that you have to put in your mind when you write a RTL code and you want to simulate it. Sorry, synthesize it. If you just want to write a code and simulate it just to check the functionality, you can write it with any of the constructs that are available with Verilog or VHDL. But if you want to synthesize your code, then there are a set of constructs that are recommended to be avoided. You should not use them. And all such set is called non-synthesizable construct. So what is this synthesizable and non-synthesizable construct? As I said, during synthesis, especially in the mapping stage, every instruction or block from your RTL code is mapped with a particular subdesign which has the exact same functionality. That means, let's say you wrote a line y is equal to negation x. Y is equal to negation x. So this instruction is actually inverting a value and assigning it to a output. Now, which standard cell has the same exact functionality? Your inverter, right? So your inverter is taken from the library and replaced. That cell replaces the Boolean expression or the instruction. Okay. Now let's say you have given assign y is equal to negation x. Assign y is equal to negation x. So here assign is a construct that Verilog gives you. Fine. But do you have any subdesign that performs this assign task? What is basically assigning? Taking a number, a numerical value, and forcing it onto any input or a wire, right? So do you have any subdesign that performs that? We don't. So that is why using assign is not recommended really if you want to go for synthesis. Now, let me make it clear. Assign values are not recommended only if they are used with numerical values. Okay. Instead, if let's say you wrote assign y is equal to a dot b, y is equal to a dot b. That is an expression that is evaluated and it does not contain a numerical value. So such assign statements can be synthesized. But assign y is equal to 1 or y is equal to 2, such assign statements cannot be synthesized. And similarly, your force release, fork join, task, all these constructs are non-synthesizable. Your always block, case, if else, or any looping constructs, all of them can be used. Okay, so that is the first thing that you have to keep in mind. Second thing, Verilog particularly allows you uh, to split down your main logic into submodules or functions. So it is important that you maintain proper connectivity between these functions or between these modules when you write the code. Only if and only if these two are satisfied, your synthesized output is clean of errors and can be carried forward for DFT and physical design. Okay, next slide. So as you can see here, this is an example to show you the non-synthesizable constructs. So in case one, you can see that we have y is equal to negation of a plus b. Okay, fine. So as per what I have told earlier, here you are only giving a expression. So the assign y is equal to negation of a plus b in case one is synthesizable, and so first a plus b is evaluated and then it is inverted during your mapping stage. A plus b is one operation for which you have your OR gate, and then the output is inverted again. So for that, an inverter comes into picture. So during mapping, for this one single line is being replaced with an OR gate and an inverter at the output. And then during optimization, your OR gate and the inverter is nothing but equivalent to NOR. Basically, OR itself is a NOR gate whose output is inverted. So that means when you go detail for assign y is equal to negation of a plus b, you are reading two inputs a and b, giving it to a NOR gate, inverting its output once, and then inverting it again for the second time. So when you go for optimization in synthesis, the two inverters are removed because it is a redundant logic. So they are removed out and only your NOR gate will be shown. Okay. Please ignore the pictures and the representation. But I hope you are getting the point, right? So if you use synthesizable constructs, your mapping and optimization will be done properly with utmost efficiency using cadence tools. But when you go to case 2, let's say you have used something called parameter, there is no gate in the library that could match the purpose of the parameter construct. So it is just left as a black box. Now by using a black box, you cannot go and continue designing your chip. So that is why your RTL code must be clean of non-synthesizable construct. Any doubts here? Synthesizable and non-synthesizable constructs? Anyone? If you have any doubts, you can post it in the chat box. Okay then. So let's continue. So that is your first input, RTL code. Now the second input is your .liberty file. So as I earlier told you, liberty file contains all the uh, functionality related information. So whenever I say functionality, I am actually referring to handling signals. How a design is handling the signals. That is what I always refer to. So, excuse me. um, I think I have a question. How value one should be defined? Sir, as I earlier said, you can directly say assign y is equal to 1 or parameter x equal to 1, where you can define a constant. But you cannot synthesize it further. If you only want to simulate it, you can do that. Basically, when you're following this procedure, the ultimate goal is to produce a chip. Okay? So when you are providing a chip and you want a constant one at any point of time, we generally directly connect it to your VDD. That's how it goes. But in a design, if you want to put it externally, it is not possible. Because that constant one has no physical physical component representation. The point understood, sir? Then, sir?
Yeah, I think so.
Okay. And so let's continue. So as I was saying, the Liberty files contain the functional information, which means the
So
way a
somebody
signal
has
is
asked
being handled.
how to define numerics. Yes. And little louder, huh?
Is it okay now, sir?
Okay. Chat box question is there.
That's what I just told. Okay, fine. I'll get back to it. Let me first this content. We're running with time. Let's get back to it, sir. So yeah, handling a signal means uh, whether the signal is being input or output type, through which pin is that being handled, and how is the switching happening. So all of this is being stored in the form of, sorry, in the Liberty file. So next slide. Right. So here you can see this is a snapshot of one of the Liberty file named slow. So and what is the information this slow.lib contains? The first one is your units of time, voltage, current, and resistance. So every value recorded in the .lib follows only these units. Okay. And then the next one is operating conditions, process, voltage, and temperature. Basically, process means the efficiency with which your fabrication is being done. Voltage is the applying voltage, and the temperature is the expected temperature of operation for your chip. So the so each one of these factor actually affects the performance of your chip individually. So if you first take process, um, uh, as an example, let's consider doping concentrations. I hope all of you are aware of doping concentrations, right? So you add impurities to your silicon in order to create excess of charge for it to move freely, right? So if this process is done with higher efficiency, then the ease of charge movement is also high. That means when a input voltage is applied, the output appears quicker. right? And the opposite is just the vice versa. And then the voltage. As you all know, higher the voltage, higher is the charge moment. And when it comes to temperature, temperature is directly associated with heat energy. And so higher the temperature, higher is the heat energy. And when this energy is absorbed by the electrons or the charge internally inside your devices, they start moving faster, right? So if your temperature is lower, the excitation is also relatively lower, and so they move relatively slower. Now the thing, one important point to be noted here is this relation or this directly proportionate relation between your temperature and the ease of charge movement is applicable only till 65 nanometer technology node. For the technology nodes below 65, uh, both higher and lower temperatures will slow down the charge. Both higher and lower temperatures will slow down the charge. The reason being, uh, for technology nodes below 65, the channel length becomes so small that the an excited charge moves in a zigzag manner, colliding with the walls of the channel and losing energy on its way. And the second thing is the temperature coefficient goes negative for those technology nodes. So that is the reason uh, below 65 nanometer, both higher and lower temperatures will slow down your charge. So depending on this process voltage and temperature as individual factors affect your ease of charge movement. I'm sorry. As all the three affect individually, when you take a combination, there will be a cumulative effect. So that means, let's say your process is 1, voltage 0.9 and temperature 125. This will have a certain cumulative effect on your charge movement. Now, if the process is 0.8, voltage 0.9 and temperature let's say 150. So in that case, you will see another level of charge movement. So like this, for different combinations of PVT, process voltage and temperature, your charge charge movement also will differ. So if you list out all the possible combinations that where you intend to check your design, there will be one combination which gives you the worst performance and there will be another which gives you the best performance, right? There will be one combination of PVT where your charge movement is the slowest, the worst performance being the slowest charge. Please note these terms to avoid confusion later for timing analysis and physical design. Please note these terms. So your worst case PVT combination, worst, gives you slow charge movement and maximum time delay. Worst, slow and max. Okay. And similarly, the best case combination, the best will push your charges faster, resulting in minimum delay. So worst, slow, max, best, fast, minimum. Okay. So because it is difficult to check your design across let's say 32, 50, 64 different combinations, we take slow and fast, only these two combinations, and check our perform synthesis and check the timing area power for only these two, for the worst case and the best case. So if you get satisfactory result in both these conditions, then your design will work fine in any other case. Okay, so that is the importance of your PBT corners mentioned in your slow dot lib. And here what you see is slow dot lib. That means a worst case scenario, and even the standard cells defined in this library will have the same switching range, very slow. Okay. So if you just look at the example of a D flip flop here, that is taken from your slow dot lib. Its area is shown to be 16.65 square micron, and the leakage power by default is 122.294 nanowatts. Now, along with these, you also have the the capacitance or the rise time, fall time, and the power indices at every pin. So here you can see the information of clock pin. So it is being taken as an input, and below you see below you can see that there are uh, matrices with one index being rise power and the other, sorry, index one and the other being value. So here the index one is your capacitance, and the values are your rise power. Similarly, you have index one your capacitance and then your fall power value. The same applies for your timing also. So under timing, you can see index one, which is your capacitance again, and the values is your rise time or your fall time. So for a standard cell, let's say it has a capacitance of 0.06 picofarad. So with that load, the time taken for the signal to rise from 0 to 1 is 0.312478 nanoseconds. And if your let's say your capacitance is 0.24, then your rise time will be 0.361. I'm referring the table at the bottom. Okay. And if your capacitance is 1.8, then your rise time will be 0.487. And if you have a value somewhere in between, like let's say between 0.06 and 0.24, let's take 0.15. For values as such, your to obtain the rise time for a capacitance of 0.15, interpolation is done. So that means for 0.06 you have 0.31, 0.24 you have 0.36. So now for 0.15, both these values 31 and 36 are interpolated and the value is calculated. So the reason why I'm emphasizing so much on this dot lab is that if you are able to understand what all the library contains, synthesis, timing analysis, and physical design can also be easily understood. So I hope whatever I've explained till this point is clear, everyone, about dot labs. So next slide. Now, after your RTL code and your dot lib, the third input is your SDC. And as I said, SDC contains your constraints or regulations that you want to impose onto your design. Okay. So to the left top, the image that you see is a snapshot of an example SDC. an example SDC. So here, um, what are the constraints that we are applying? In the first line, you can see we are creating a clock and naming it CLK. And we are also mentioning that its period is 2. That means its time period is 2 nanoseconds and waveform is 0 to 1. That means the pulse width, that means the on time is from t is equal to 0 nanoseconds to is equal to 1 nanosecond. Out of 0 to 2 nanoseconds time period, 0 to 1 is your on time. That means the remaining 1 to 2 will be your off time. Okay. So, and we are applying this waveform to our port CLK. Where did you get this port name? From your RTL code. Okay. Now, similarly for your clock, you are mentioning the rise time to be rise time and fall time to be 0.1 nanosecond each. That is 100 picoseconds. And then you also have input delay and output delay. Here you are mentioning it to be maximum 1 nanosecond. So like this, you can also mention what is the maximum capacitance for any cell in your design, or what is the maximum leakage power that you can permit, or what is the operating conditions that you intend to use, what is the maximum load that any cell can take up. So like this, relating to your operating condition, environment, design rules, power, timing, etc., you can apply certain constraints onto your design. It is the designer's job to understand the design, to understand its specification, and accordingly bring out the SDC. Okay, so SDC is basically optional. Synthesis runs synthesis runs even without an SDC with some default values, but it is very strongly recommended to frame a file to about whichever design you use. The only thing is, if your design involves a sequential cell, if it involves a clock, you can name it. Else, if it is a purely combinational design, then maybe you can exclude all the constraints related to a clock or anything related to that, and maybe stick to only your design rules, power, your wire load models, environment, or operating condition. Okay. Um, yes, for different technology nodes, you'll be having different .lib files with different values for each design and its pins. And yes, the constraints applied during synthesis will help the process. As I earlier said, your synthesis happens in 3 stages: translation, mapping, and optimization. So whenever mapping is being done, uh, let's take the same example. If an instruction y is equal to negation x is being mapped to your liberty file. So your liberty file may contain several inverters, each one having the same functionality but different driving strength. Driving strength is a measure of pushing a signal outward as an output at a certain load. Higher the driving strength, higher is the load that can be driven. So, uh, so obviously, the power consumption also will be high, and the cells with higher driving strength are relatively larger than the one uh, with lower driving strengths. So when you actually put these SDC, let me take this example. Um, let's say I've put a constraint, set max fan out to be 4. Set max fan out to be 4. So without my SDC, without if the SDC is not given, my EDA tool can actually map y is equal to negation x to the highest driving strength inverter and use that in my final gate level circuit. But if I put a constraint, set max fan out to be 2, 3 or 4, then it will restrict during that mapping process, your tool will restrict to lower driving strength cells. Because of that, your area consumed will be lower, power dissipation will be lower, and your timing also will be quicker, because smaller cells give smaller delays. So is that understood, sir?
Yeah, fine. Thank you.
Okay. So any more questions with respect to the inputs? Fine, then let me continue. So apart from these three, this is just for your information. If you are using logical synthesis, you'll be taking only RTL code, Liberty file, and SDC. In case there is another form of synthesis called physical synthesis, which is very much analogous to physical design. Okay, to keep it simple, physical synthesis is like running a rough estimate on your PD, on your physical design. So when you're dealing with either one of these stages, you include dot left. So as I earlier said, left contains all the physical layer information and its dimensions. So obviously it is given by your foundry. So maybe your Liberty files could be given by your vendors, but dot left must come from your foundry, the concerned foundry. So TSMC will have a certain setup to fabricate your chip. Global foundries will have another. So like that, the left files, which whatever they give, will contain slightly different dimensions. Okay, because it is foundry dependent. Next slide. So whatever foundry left you are taking, your fabrication also will happen exactly at the same place. You cannot use a left file from TSMC and fabricate your chip at global foundries. Okay, that is not allowed, and even if you try to do so, your chip will not be fabricated properly. Okay, so just to show you, you will be having all the list from oxides, polysilicons, and metals. So depending on the foundry, your metal count might range from metal 1 to metal 6, 9, 12, 11, 12, 15, 16, 32, 64, etc. Okay, depending on the technology node as well as the foundry type that you're using, the number of layers will differ. And for each layer, especially the metals, you will be having a detailed tables of what is the minimum dimensions that are to be maintained. The minimum width, the internal minimum width of a metal layer, as well as the minimum spacing that is to be maintained between two different layers end to end. Okay, and similarly, if you have a via, what is the minimum enclosure for that via? What is the minimum dimension on all the four sides are also given in your left files. Okay, next. know I'm going a little too deep, but it is important for you to understand each one of this uh, for a clear understanding on how it is implemented onto the tool. Okay. So with this, with all these inputs, your um, synthesis process will be done. And once synthesis process done, you will also perform timing analysis. Okay. So just some general guidelines to help you avoid the to help you avoid the common mistakes uh, that are done during synthesis. SDC must be SDC can be applied for a purely combinational cell, but uh, but applying an SDC with constraints like creating clock or anything related to that is a mistake. If you're having a purely combinational design, make sure your SDC is free of any clock related constraints. And when you're reading these files, you generally um type down the paths where these files are present. So there could be mistakes in the spellings or the case sensitivity as you give the path. So even that has to be carefully taken. We'll anyway show that. And so here we read all the inputs in a chronological order. All the synthesis as you execute it on the EDA tool goes in a chronological order. So that order should never be disturbed or shuffled. The reason is we created an order where first all the inputs are read, understood by the tool, and only then your synthesis runs. So if you shuffle it, your tool will simply throw an error because it does not understand what you're trying to do. Okay, and the most important, having non-synthesizable constructs in your RTL code. You may be able to simulate it, but you cannot synthesize it. So you have to take care of it. And then the output files that you get is your netlist and block level SDC along with your area timing power reports. So during our tool demo, we shall look at each file, its content, and its content for both inputs and outputs. Next. So for this synthesis process, we are going to use Genus synthesis tool. So Genus is a industry grade, Cadence Genus is an industry grade tool because of its high productivity and efficiency. And the best thing is that right now the tool that you have at your institution can actually use can actually synthesize 10 million instances flat. Okay, depending on the licenses you have, you can even go further. Next, for anyone who is using Encounter RTL compiler and Genus are just the same. Genus is the next version. That's all. Okay. So how are you actually performing the synthesis on the tool? You first read your .lib file, and then you also read your RTL code, and then elaborate your design. That means you'll ask the tool to first understand what is present in the Liberty file and what is present in your RTL code. Then you read your SDC file and then perform generic synthesis where translation happens and your mapping is also done. So during this mapping between your RTL code and your Liberty file, your SDC will act like a filter to give you only the most efficient standard cells. Okay, and once mapping is also done, to remove the redundant logic, your optimization is done, and whatever final gate level circuit you have is recorded in the form of connectivity into a gate level netlist. And also you will have your timing area power reports along with block level STA. So this is the flow that is recommended, and shuffling any of this will actually throw errors. So hence it is not, hence please avoid that. Okay, next. So if you want to use the Genus tool, you can, by default, GUI is not visible. It's a command-based approach. So you can use Genus-GUI to directly open it with the GUI and then execute all the commands one by one to execute the flow. Or another way of doing it is uh, compiling all the commands in a chronological order into a tickle script. That means it's just a text file where all your commands are noted down. Okay, tickle TCL stands for tool command language. So using a tickle script will help you automate the process with executing all the commands one after the other automatically. Okay, so if you want to execute the flow with individual commands, you can just invoke Genus and its GUI as an option, execute the commands one by one, or you can directly open Genus with -f extension. F means file, and directly read the tickle script file. So even that way you can run it. Okay. Next. So that is all about your synthesis. Okay. So any doubts till this point?
Hey, Krishna, you have to meet at 2 o'clock. Again,
Sorry, sir.
Sai. Hello?
Yes, sir. Yes, sir.
There will be a break, don't forget.
No, sir. I remember that. I wanted to break it now here.
Acha. Okay.
So I'm just asking till this point, is everything clear with everyone?
Okay. Because what happened yesterday, no, there was a morning session from Mariam, Dr. Mariam Antibody professor. She has requested evening 1 hour session because she could not complete her topic. Evening again
Okay.
5 o'clock, again they will have 5 o'clock 1 hour session at least. So,
Okay. No problem, sir. I am following the
yeah,
script
okay.
that you have given.
Okay. Okay.
Please don't worry about it.
Okay.
This static timing analysis, I will break now. And after lunch, for the first 20 minutes or so, I'll cover the static timing analysis, the theory part and the concept, and then we'll switch to demo.
Okay.
Demo of RTL coding, functional synthesis, sorry, functional simulation, synthesis, and STA. Okay. Before we break, any questions till this point? From anyone, if there is anything, you can post them in the chat box or unmute yourself. If you have nothing, at least let me know that.
Saya, I think no question. No questions.
Okay, in that case, I believe everything is clear till this point and you have understood every point, what is what is it, why we use it, and how we do it. So with that, let's break for lunch. Sir, till when is the lunch break? 2 o'clock, right?
2 o'clock.
Yeah. So let's assemble back at 2 o'clock, and that's it. First 20 minutes for static timing analysis, then the demo.
Okay.
Thank you, everyone. Let's
Thank you, everyone. Break. Please assemble at 2 o'clock. We'll have 2 to 4 session by Entuple. And then again, small break at 5 o'clock. We'll have math session. I'll close this meeting, okay? Don't remain connected. I'm going to close this meeting.